Welcome everybody to today's seminar. Our speaker today is Paolo Glorioso, who has recently moved to Stanford. So we all know him from his very famous review that we on effective field theories on Schwinger-Keldysh contour, which many of us have read and studied, and he has pioneered many of the works on that frontier. But today he's going to talk about something different. It will be on hydrodynamics or how hydrodynamics breaks down for Fracton fluids. So we are very interested in that. And so Paolo, over to you now.
Thank you. Thanks for the invitation and for the introduction. So yeah, so today I will talk about essentially the hydrodynamics of fractons, as well as its interplay with the renormalization group effects and ultimately the breakdown of hydrodynamics. And we will see some funny features that arise as a consequence of this fractonic behavior. So this is work from last May in collaboration with Jinkan Guo, Andy Lucas, and Joaquin Rodriguez-Nieva. So fractons, as we know, fractons are another kind of quantum matter. I would say the characterizing feature is that the behavior of the excitations is subject to constraints. So the mobility of these excitations is constrained. A simple example, which I will discuss in more detail throughout the talk, is when we have, say, a conserved scalar charge in one dimension, for example, together with the associated dipole moment. So the dipole moment of the charge is also conserved. And as a consequence, the mobility of each individual particle is restricted. In particular, a single particle cannot move from this site to this site. That's because it violates a dipole conservation. So this type of restricted mobility in excitations has been appreciated for at least 15 years. But in the last couple of years, there has been a huge increase in interest in several directions, starting with quantum information, in particular in relation to classifying topological order, topological phases. Another direction, which we mentioned earlier and we had a talk about, is the connection with elasticity and the gravity, where we have, this is description in terms of higher rank symmetric gauge fields, which can be interpreted as some sort of deformation of a metric. And then another context is that of thermalization, a little more recent, I would say, where, so the intuition here is that the restricted mobility of the particles induces a slower thermalization. Okay, so there are no trivial collective phenomena here. Another context is in quantum field theory, where several groups, starting with Seiberg, basically translated these lattice models into continuum field theories, which display several exotic properties, and we have seen new dualities being uncovered. Good. So in the last year and a half, roughly, there has been also lots of progress in understanding the hydrodynamics of these, the collective hydrodynamic behavior of these systems. In particular, there was an experiment from a group in Princeton. I would say the first experimental evidence of fractonic behavior, really. So in this experiment, so this was in the context of ultra cold atoms. Basically, this group considered a chain of fermions undergoing some Fermi-Hubbard dynamics. So this H0 is you can imagine some lattice fermion Hamiltonian. And then this dynamics is subject to a strong electric field. So here F is really the electric field with a linear potential. Okay. So the idea is that if I take F sufficiently strong, then this dynamically imposes the conservation of the center of mass, okay, because this is just the integral of a position. But the center of mass here is actually the total dipole, because the charge is just the number, the particle number. So the dipole is the center of mass. It's just the sum over all the positions. So if we have this conservation of the dipole, then that's an instance of fractonic behavior. It's precisely what I mentioned here. Good. So what was observed in this experiment is that, first of all, what was measured was the response in the charge sector, meaning we look at basically at the dispersion relation for the charge transport. Usually, hydrodynamics predicts it to be quadratic, meaning omega goes like a momentum, the frequency goes like momentum square. Instead, here, for sufficiently strong electric field, it was observed k to the fourth. Okay, so we have a different dynamical scaling, as this graph shows. We flow from 2 to 4 as we crank up the electric field. So it turns out that this higher scaling is a hydrodynamic avatar of fractonic behavior. Okay. Now, these higher scalings were more systematically understood in a subsequent theoretical paper. And then they were further explored by several subsequent works up to very recently.
Paolo, can I ask the question on the plot that is being shown? So what is the x-axis here?
The x-axis is the electric field F.
I see. For a sufficiently large electric field, you get a k to the power 4 scaling.
Exactly. Yes.
I see. Okay, so why it is like that? You know, like why not for smaller electric fields?
Right. Yeah. So if you take F to 0, say, then you just have, you just have a strongly coupled dynamics, which conserves U1 charge, which is just the particle number. And that by, Landau type of arguments, we know that it should go like k square. So we definitely want k square. But then if F is, so if F is taken very large, then this center of mass position is basically frozen. So the particle, for example, you cannot have this type of single particle motion. That they have to move in tandem, so to say. And the effect of, so basically the dynamics is slowed down by the strong electric field. And the slowdown corresponds to a higher power in momentum. Because here we are at low momentum. So if you take a higher power, the frequency will be smaller. If the frequency is smaller, the dynamics is lower.
I see. Okay. So you can similarly put higher order multipoles here and you see different scalings. So when the corresponding coupling becomes large. I see.
Yes.
Thanks.
Yeah, the experiment was on simple, just the first dipole, say no quadruple or something. But yeah, in principle, like here you have these 2 times n plus 1, and that's as you conserve higher multiples, that's what will happen. Good. So until now, translation invariance has not been included in this transport, hydrodynamic, and so on. Now, including translation invariance is relevant if we want to deal just with many particle systems that are not necessarily coupled to a lattice. It's relevant for continuum quantum field theories, and maybe in general for systems that in some temperature regime have some emergent quasi-conserved momentum. Okay. We'll see an example later of this last instance. So the first goal will be to formulate a general theory of hydrodynamics for fractons, in particular with translation invariance. Now, this will turn out to have very peculiar properties. Essentially, for a very basic reason, our input will be this symmetry algebra. So this is the commutator between momentum and dipole, and this is not trivial. So this is an extension of space-time symmetries. There is an interplay between space-time and internal symmetries. And this will be really responsible for everything. The second goal, and I would say this was actually my original interest to get into this, is the search for new dynamical universality classes. So what do I mean here? Well, so we know that the late time dynamics of systems that thermalize, the dynamics is described by, generically by hydrodynamics. But then we define hydrodynamics as a set of equations of motion, usually. However, this dynamics is accompanied with fluctuations. Fluctuations can arise because the system is at finite temperature, and they can arise because sometimes the system is quantum. And in some situations, such fluctuations infer very dramatic effects. They end up completely qualitatively changing the predictions of naive say mean field hydrodynamics. Okay. So this type of phenomenon was first discovered more than 50 years ago numerically in simple hard sphere simulations. But now let me show you to get a better sense of what this type of mechanism is about. Let me just basically explain a list of contexts where this has been uncovered from quite some time ago to last year, basically. So probably the most known situation where fluctuations destroy basically the hydrodynamics as a local theory, as a local equation of motion, is that of just ordinary fluids actually with translation invariance. The caveat is we need to be in sufficiently low dimension. That's kind of reasonable, right? Because if we go in low dimension, it's more possible to have relevant operators in our RG. And relevant operators can drive strong fluctuations by definition as we go to the IR. But hydrodynamics is defining the IR. So that's where things break down. And in particular, what was found is that in one spatial dimension, dissipative transport coefficients, such as the bulk viscosity, say, diverge with the system size. So hydrodynamics, again, is not well defined here, strictly speaking. In particular, the divergence is given by a universal exponent. And this exponent can be related to the famous Kardar-Parisi-Jang universality class, KPZ universality class. It's a famous universality class in one dimension for stochastic systems. I will talk more about this later. Another context, and in two dimension is marginal. The hydrodynamics is marginal, and we have a logarithmic divergence, so slow, but it's still slightly singular. Another context is that of spin chains. We have, for instance, integrable spin chains with SU2 symmetry. So at half filling, meaning at zero magnetization, it's been shown numerically and later understood theoretically that particularly at the half filling point, spin transport displays again this KPZ scaling. So KPZ again is this Kardar-Parisi-Jang universality class. So this exponent 3 halves is actually the same as this 1/3. It's just different observables, but it comes from the same universality. Okay. Another context, still in spin chains, is that of integrable spin chains. For some particular models, in particular XXZ classical chain, it's been observed that in a suitable temperature interval, there is an emergent almost conserved quantity, which looks a little bit like a conserved momentum. And again, this displays in the low energy KPZ scaling.
Paolo, can I ask something about this k to the power 3 by 2? So this L to the power 1/3 is to some kind of anomalous scaling with respect to k, or what is this?
Yes, you can imagine it as we define some local theory as some intermediate scale, which is higher than where this thing shows up. And then by doing loop effects, well, this is not perturbative, but anyway, doing some resummation, loop effects, etc., will give rise to a finite correction to the scaling dimension, leading to this finite anomalous correction. But does that? Yeah.
Yeah, I understand. So you have to do some resummation over k and
yes.
resummation over k and then to get you get this power, like anomalous power.
Yes. Yeah, you have to resum infinite Feynman diagrams, and it's rather non-trivial. And it only, as far as I know, it only works for when you have this universality class. Because of some there is an accidental emergent symmetry in the far IR, which allows you to actually compute these exponents. Yeah, it's a very beautiful story.
Yeah, thanks. I didn't know about this work at all. Very interesting. Okay, I see. Thanks. Okay.
So another completely unrelated context is that, so it's actually, I think this is the simplest context within hydrodynamics. So basically, imagine we just have a single conserved charge. There is no momentum. It's just a scalar U1 charge. But this conservation is subject to chiral anomaly. And then one can show that in one dimension, again, charge transport will flow to this KPZ universality class again. So in this case, it's an interplay between, quantum anomaly and the thermal fluctuations. In any case, the end result in the far IR is still the same fixed point we found here. And then in 2 dimensions, we can engineer an extension to 2 dimensions of this sort of dynamics. I will actually, if there is time, I will give some more details about this part. 2 dimensions is marginal, and then in higher dimensions, the fixed point is trivial. So this is just a graph showing. So the y-axis is just qualitatively indicating that whether we have a non-trivial fixed point. So if the dot is different from 0 on the y-axis, it just means that the fixed point is strongly coupled, is non-Gaussian. If the dot lies on this line, it means the fixed point is trivial. That's all this graph means. So the take home I wanted to get from these 2 slides is that so far within hydrodynamics, the only strongly coupled universality class is KPZ in 1 dimension, or coupled KPZ. Whereas and the upper critical dimension is 2 spatial dimensions. But then so of course hydrodynamics is a universal theory. So is this really all we can get? Can we somehow hope to qualitatively change the picture of this diagram? In particular, can fractons lead us to new universality classes that just allow us to deviate from this scenario? So the reason why this question makes sense here is inspired by the experiment that I described in the beginning, which showed that this higher scaling. Okay, so this higher scaling is not due to fluctuations. This is really a mean field thing. There are no loops here. There's no randomization. However, the fact that we already have a different scaling at mean field level means that probably if we study the RG flow, something very dramatic will happen compared to any other thermalized system we know of. So we will indeed see that the answer to this question is yes. So I will explore what we end up getting and what are our predictions. So here,
sorry, Paolo, can I ask something maybe very elementary? So in this context, what is where should hydrodynamics apply? Because we don't, is there something like a Gibbs equilibrium, or what is it?
Right, yes. So I'm assuming that the system has undergone thermalization, meaning, the underlying dynamics is sufficiently strongly coupled. It's not it's chaotic. There is some conserved quantity to talk about, which will define the Gibbs ensemble, a local Gibbs ensemble. So this Gibbs ensemble will develop after some thermalization time. Right, and then at that point we will be able to talk about hydrodynamics. And subsequently, we will see how then hydrodynamics actually, at even later time, we will see how hydrodynamics breaks down. So basically, first you have thermalization. After thermalization, the surviving degrees of freedom will just be, whatever long living operators are in your leftover dynamics. And these generically will only be conserved quantities. That's because I'm assuming the system is chaotic. Then I'm going to write down an effective theory for the dynamics of these conserved quantities, which holds after the thermalization time. Okay. But then if this should be a self-consistent description. And then we'll see that if we account for fluctuation effects, this description will actually lead to a non-local dynamics, despite hydrodynamics in the first place is a local theory.
So your assumption is that that Gibbs equilibrium is sort of a metastable state that should exist. That's
that is there. It is stable.
Oh, okay.
Let's say the drama, really what these fluctuations will change is the
dynamic. Scale of non-locality. You're thinking there's some scale of non-locality after which your theory.
It's a non-locality in time. It's a non-locality for dynamical processes. So basically, your state, the state is well defined. This Gibbs, it's fixed. It's stable. In this RG sense, it's stable. However, when you look at dynamical correlations, so just correlations in time, these will differ from the naive predictions of a mean field hydrodynamics. If hydrodynamics,
but only at a very long time.
Only a very long time.
Yes. Long time. Yes.
Yes.
Okay, they will have these tails. You mean there will be long tails which are not captured by hydro? I see.
Exactly, by mean field hydro.
Okay.
Exactly.
Okay.
Exactly.
Okay.
Yes.
Thanks. Okay.
Good. So the first part will be about the naive description. I mean, of course, this is naive, but it holds true as far as we are not at too long scales. And moreover, this will really, outline the main characters of the story, symmetries, degrees of freedom, and so on. In the second part, I will outline basically an action formulation for this Fracton hydrodynamics. This will be useful later on to systematically describe the effect of fluctuations. And then fluctuations will lead to the breakdown of the naive local hydrodynamics. So there is, eventually it turns out to be a self-consistent description, but it's different from mean field hydrodynamics. And that's thanks to this more systematic but integral approach. Okay, are there further questions so far? Okay, so let's start with this, phenomenological approach. Basically, I'm going to follow roughly the lines of Landau, but we'll see that there are several caveats in trying to, enforcing them to apply to fractons. Good. So our starting point is the symmetry algebra. Again, I'm assuming that we have translation invariance, so we have momentum, and then we have a conserved scalar charge coming from maybe a U1 symmetry, and also the associated total dipole. These are our three conserved quantities, and they obey this trivial algebra, this Heisenberg algebra. So let's try to familiarize with this structure. So let's look at two simple examples. So the first example is that of a charge operator in a quantum field theory, which has this, dipole symmetry. Now an example is that instead of having just this global redefinition of the phase, which is constant, the phase for these particular field theories can depend linearly on X. It turns out that this additional symmetry is related to conservation of the dipole. And then, if we just do the algebra, we write down the infinitesimal transformations because so this is the infinitesimal dipole phase redefinition. There is an explicit dependence on X, which comes from here. But then because there is an explicit dependence on X, the commutator with momentum is not zero, obviously. So we end up with this, which is exactly this commutator. So another example, we can consider just a system of classical particles, say like in some kinetic theory, where particles are described by position X and P and momentum P, and K labels the particles. So the total momentum is just the sum over P. The dipole is the sum of the charge of each particle multiplied by the position. And then if we look at the Poisson bracket between X and P, it's just the canonical one, and we apply it to the total momentum and dipole, then again we end up with this algebra. Okay, so really this algebra is the statement that D is the dipole associated to the charge Q. Okay, so you can take it as definition of the dipole. Now let's look at two concrete models, which may look a bit exotic. So two models that realize the symmetry and that we actually used to implement numerics and double check our predictions. So the first example, we can imagine a classical chain of n particles. So let's say xi labels the positions. And then this potential, just tells me that consecutive particles will interact in a translation invariant way. And then instead of the usual kinetic term, we have this coupled momenta kinetic term. Okay, so this kinetic term has been engineered so that we basically have a translation invariance in momentum space. And one can show that, just Noether's theorem, this particular shift invariance leads to the conservation of the center of mass. Okay, but now each particle has charge +1, so the center of mass is the dipole. Okay, so this symmetry is engineered so that we have conservation of the dipole. Now, if this model looks a bit exotic, let me just mention very, very briefly that if I linearize this Hamiltonian, if I linearize the potential, then this Hamiltonian looks identical to this one with the same canonical commutation relations between these variables phi and s, where phi and s describe the the spin vector in the Heisenberg Hamiltonian. So if I linearize the Heisenberg Hamiltonian dynamics, I get something that is identical to my exotic dipole conserving chain. So maybe this is not too exotic after all. However, yeah, the agreement is just a linear level, I should mention. Okay, so now in this chain, we have three conserved quantities. We have momentum, we have the number of particles, of course, and then again we have total momentum. Now, the fact that the center of mass is constrained precisely characterizes the restriction in the mobility of my particles. This can be equivalently interpreted as stating that the mass of the center of mass is infinite. Okay, so the center of mass cannot be moved. And that's why the position is preserved. In particular, the dynamics is independent on the total momentum. So this is a bit related. People often talk about, one reason of studying fractals is that they have such a high degeneracy. And if you like, this is a baby example of the degeneracy. The energy does not depend on the total momentum. And then we have another model I won't mention much. It's another chain which is, however, inspired by the experiment I mentioned in the introduction. So we hope that this actually can find an experimental implementation. This model has an emergent dipole conservation as well as momentum conservation. So in the IR, this will look like what we need. This will have the hydrodynamics that I will talk about. Okay, so enough of model building. Let's look at the general setup. So I'm going to outline how we write down basically this hydrodynamics for space-time symmetries with a non-trivial extension of the algebra. So this is what we mentioned earlier. So we assume we are at some, we are interested in time variations of the dynamics that are long compared to some characteristic time of the system. In particular, if this is the microscopic time, maybe some mean free path, or maybe in a CFT, it could be 1 over the temperature. Anyway, some microscopic dimensionful parameter. We assume that the state varies on scales that are much longer than this microscopic scale. And moreover, we assume that over these, sort of mesoscopic regions, thermodynamic quantities are well defined. Okay, so in particular, locally, we have a well-defined Gibbs ensemble. So here in this case, we have.
Paolo, again, just a stupid question, maybe to go back to your early models that you described. So basically, this new symmetry has a non-trivial bracket with translations. So is there a way to think about, like, suppose I have a field theory description to preserve diffeomorphism and variance and compute T mu, the stress tensor or something like that you need to?
Yeah, that's a very striking question. So you may know perhaps that there is some tension with preserving this dipole symmetry together with having a generic metric. So that's still an open question. It's not known how to do. So basically, what you can hope to do, and that's what we'll do here. You can basically do a dynamical theory of coordinate transformations. The metric is still flat, but you can introduce coordinate transformations, and those will allow you to extract the stress tensor. I don't know if this answers.
Okay. Okay. Thanks. Thank you. Yeah.
Yeah. The stress tensor.
So you cannot. Yeah. So
Sorry.
there is no way you can gauge both the symmetries together in a fictitious way and extract something like
yes.
this.
It's not a theorem, but it's an open question how to do it. It's not clear.
I see. Okay, thanks.
And maybe just to clarify, let me just mention it's different from, so like in elasticity theory, where we compare these higher rank gauge fields to a metric, that's a completely different situation. The metric there is a dynamical field. It's related to, the metric itself is related to the conservation of the dipole, of higher dipoles. Whereas here, I'm talking about the dipole conservation and separately diff invariance. So it's, structurally speaking, it's a very different. Yeah.
So basically here, of course, if you have to gauge one, you have to gauge the other two because they mix, and that's the harder. That makes it hard. Actually, yes. That's the main. Yeah.
Good. So great. So good. So the Gibson sample here will be, maybe we have a Hamilton, maybe we have a conserved energy. We may not. Let's say we do. We have a conserved charge. We have a conserved momentum. We have a respective chemical potentials. So mu for the charge and VI, which is the velocity for the momentum. And then in principle, we can add the total dipole with the respective chemical potential, but I will soon show you that that's actually not necessary. Basically, upon thermalization, the dipole charge becomes, it's not an independent degree of freedom. It's basically described by the charge itself. I will show you in a second what that means. Good. So first of all, for simplicity, I will neglect energy conservation. Remember, we are going to build up an effective theory for conserved quantities. I want to be as simple as possible, so I will ignore energy as a conserved quantity, although it might be there. One can view this as a sort of the coupling limit. It is perfectly realizable. I will just be interested in the dynamics of charge and momentum. So what we do in hydrodynamics is we introduce the densities, the local densities, right? Because the dynamics, at least a priori, is local. So we should be able to define local degrees of freedom associated to the corresponding total charges. Now, as I mentioned, there is no independent dipole density. Now, it turns out that the total dipole charge is given by simply this integral at late time. We can understand this integral as just summing over all the charge or the particle positions times the charge at the given location. It turns out that actually this is in principle this doesn't have to be true. In principle, we can have an additional maybe internal or some sort of internal degree of freedom that is separate from the orbital location of the particles. Like in angular momentum, with some orbital angular momentum and internal spin. So one could, in principle, say, "Oh, wait," but then I could have an additional degree of freedom describing this total dipole. That's you can easily come up with such a model. However, if you wait a sufficiently long time after thermalization, you see that even before thermalization, doing a thought experiment, you can see that you can easily come up with processes that, they conserve the total quantity, this one here, but they don't conserve SI, right? This is just some, if you look at this picture and you think about a little bit about this, you'll see that, this SI before the transition is 2, and after transition, it changes to a different value. So in other words, this SI is not conserved. But that means that if I wait a sufficiently long amount of time, this SI will decay. It will not be part of hydrodynamics. And if decays, then it means that this expression is correct. Remember here, we are not doing a rigorous derivation of the hydrodynamics. This is more of a heuristic approach. Later, we will see with this effective action approach, things will geometrize completely, and actually this will emerge this will be recovered in a more geometrical fashion. Good. So now we understood, we sort of identified the degrees of freedom, momentum density, and charge density. And now we want to understand the dynamics. So the dynamics is dictated by the conservation equations. Of course, here we have many components. Like we have all the components of the stress tensor. We have all the components of the charge flux. So what we do in hydrodynamics is we need to close the equation by expressing the currents, the stress and the current in terms of the actual hydrodynamic degrees of freedom, meaning pi and n, okay? And that's simply because the current is not a conserved quantity itself. So as we wait time long enough, it will be dominated by, by its overlap with the momentum density operator and with the charge density operator. Okay. So that we can close the dynamics. So basically what we do from this, we are doing some sort of effective field theory, right? At the level of equations of motion. So, so what we want to do is basically we write down explicit expressions of, say, the stress in terms of pi and n that are consistent with symmetries and with the other basic requirements. So let's now look at the symmetries. First, recall we have this algebra, but now this algebra translates into algebra for the densities, where here we have commutator between the total dipole and the momentum density, and here we have the charge density. So if I take the spatial integral of this equation, I just get back my, our starting point, the starting algebra. Another way to state this commutator is that upon dipole transformations, the momentum shifts by an amount that is proportional to the charge density. So it's a little bit of a funny nonlinear transformation. It's almost, this is kind of deceiving to say, but it's almost like a Goldstone mode, if you like. It's not a Goldstone mode, but it looks formally a little bit like that. Now, as a consequence of this invariance and through consistency with the conservation equation, with the word identity, one can infer that the stress tensor, and this goes back to your previous question, Ian, the stress tensor transforms non-trivially as well. So it shifts by an amount that is proportional to the, well, it's linear in the charge current. Now, this doesn't look like a symmetry, like it's symmetric, right? So what's happening here? Is it that the stress tensor is not symmetric? Is this related to, the obstruction in coupling the theory to a curve metric? So actually, we are dealing with the rotational invariant theory. We are assuming we have rotational invariance here, so the stress tensor should be symmetric. So how do we reconcile these two things? This took some time to figure, but the answer is, of course, very simple. It turns out that the charge flux is a total derivative. There is a more physical way to see that. Regardless, if this is a total derivative, then it means that we can hope that the anti-symmetric part of the stress tensor is a total derivative itself, because this C is a constant. It's just a, just a parameter of the transformation. And indeed, so it will turn out that the stress tensor is symmetric up to total derivatives. If you have a flat metric, that's fine. That's perfectly consistent. Good. So maybe let me skip a bit ahead. Oh, right. So, okay, let me mention, so a consequence of this nonlinear shift is that now when we go to look at the consistency with thermodynamics, okay, we started from this first law of thermodynamics, which relates entropy density to, scalar density and the momentum density. Now we are going to take the entropy density as our thermodynamic potential. So basically the static content of the physics of the low energy observables will come from this thermodynamic potential. Usually the entropy density, is a function of n and pi. But here, because of this shift symmetry, it is going to be a function of derivatives of pi, or more precise, derivative of pi over the density. So this is a very interesting physical consequence. If we now use this thermodynamic relation, we can see that the velocity of the system, of the fluid, is proportional to the momentum, as it should, but there is an overall derivative factor. Okay. Usually the velocity is proportional to the momentum, and the relative factor is the inertia. Is the inertia density? It's like the mass density of the underlying fluid constituents. Just some particle mass density, basically. Here instead, it's a Laplacian. It's basically, it's a second derivative. So what does that mean? Well, so this is, we can interpret this as saying, so here you have momentum. So this is essentially 1 over the mass. So this is saying that as we are interested in, so if this is the momentum of a region of size, of some size L, the mass, or 1 over the mass, is going to 0 as L square, as 1 over L square. Or the mass is diverging. The mass of this subregion of length L is diverging with the system size square. Particularly, the total system will have infinite mass, infinite inertia. But that's exactly what came out of this, of these models before, where, or the experiment from the Princeton group, where we said the center of mass is conserved, and it can be interpreted as the mass of the center of mass being infinite. So again, the total system has an infinite center of mass, has an infinite mass. Here we see that we are generalizing that notion to subregions of the system. This is saying that subregions of the system have a finite mass, but it's divergent with the system size.
Yeah, but isn't this a little funny, because the momentum density is a fundamental operator, whereas this V or mu or T, these are like thermodynamic variables. And here you're saying that somehow the operator dynamics is completely determined by some emergent variable, or
Yes, it is very confusing. So if you want to write down the partition function of the system, you just integrate over everything. Remember, there is this degeneracy where the dynamics is independent of the total momentum. It's just because of this shift symmetry. So this degeneracy leads to a divergence of the partition function because of this degeneracy. The divergence in turn can be connected to this tension with locality. Why is it a tension with locality? It's tension with locality because if you want to write down the entropy density as a function of chemical potentials rather than charges, you can go to grand canonical ensemble and just write, S as a function of mu and the velocity. Here you cannot do it. If you do it, you will, at best, you should expect a non-local expression, because you have gradient of pi, but pi is the inverse Laplacian of V. So this will be schematically some inverse derivative of V. So it's non-local. And this is connected to the divergence that you obtain when you compute the partition function, and the divergence is due to this symmetry or degeneracy. So I agree, it's strange. But then all the ingredients are patched together. And again, this just comes from this slowdown of the dynamics, as well as this degeneracy of the energy.
So you're saying this non-locality is connected to this enormous degeneracy?
Yes, exactly.
Nice. Interesting.
Yeah. So like I said, you can try to apply, very old arguments, but you needed to revise each of them very carefully. Anyway, we did numerics and we obtained, let me maybe skip a few details. Right, so through these considerations and further consistency conditions with thermodynamics, we can write down the nonlinear dissipative hydrodynamics. Now, one thing that comes from what we just discussed, so we can look at the equal time 2-point function of the momentum density. Again, this is the interpretation of the mass density of a system, of a subsystem of a size k, 1 over k. And as you can see, we have this divergence 1 over k squared. That's exactly what we were discussing. And in simulating these two models I discussed before, we indeed do see exact consistency with this non-local trend.
Okay, that's exactly this Laplacian 1 over k square that you are finding here. So
right,
what is it that you have?
Sorry.
So you have simulated the first model that you had just n particles with conserved, where this total momentum is not related to. I see.
Right.
Very interesting.
Yeah, so this is like a log plot, and the coefficient is -1, -2, I guess, -1/2, -2. Yeah. Yeah, this is this is not log plot. Yeah, again we see.
But could you go back to, sorry for this, I mean, probably wanted to skip for lack of time, but this partition function, so your consistency with, how do you get this consistency condition that leads you to this expression for T mu?
It's, yeah, you put together this symmetry together with the first law of thermodynamics, basically. Yeah, so this relation. Yeah, I mean, there is some algebra. It's not, well, okay, maybe we can see schematically why that's the case. Yeah, just take, so first of all, your thermodynamic potential, you know, this is an observable, so it must depend on derivative of pi over m, right? Because, you know, you want this symmetry. And then from this relation, we see derivative of s with respect to pi gives the velocity. But then, you know, say, yeah, yeah, right, it's this one. I mean, because you have a gradient here, then when you take the derivative, if you write down an explicit term, for example, gradient pi square, right? For rotation invariance, that's the lowest order in derivative you can write down, because you need to contract the indices. So gradient pi square, and then you take the derivative, and you end up with the Laplacian of pi. Yeah. Right. So then there is a mechanical way to relate this Laplacian to this 2-point function, like the 1 over k squared here must be there because you have a Laplacian there. This is also called momentum susceptibility, if you like. Yeah. Okay. So maybe I will go very quickly through this because I want to get to our predictions. So I'm going to, you know, outline now a functional, a path integral way to rederive this Fracton collective hydrodynamics. And then we will use this path integral to figure out the renormalization group. And then we will see, you know, these anomalous scalings emerging and so on. So good. So, okay, let me just say a few words. So we are interested in writing down a path integral for this hydrodynamics. So that means we need a path integral for mixed states. Okay, so that's not like vacuum to vacuum amplitude. This is more like an expectation value where the initial state is, in our case, is some local Gibbs ensemble, such as this. But now, you know, if we have a mixed state, it will evolve by conjugation with the unitary operator. So we have in particular 2 factors of the evolution. But then if we convert this evolution to a path integral, it means we need the 2 factors of the 2 measures. You know, we need to double up the evolution. So the minus here in particular is because we have the backward time evolution on the second part. So in pictures, we just write a contour of this form, where at the final time we identify our quantum fields. That's just because I'm taking the trace. Okay. So anyway, we're dealing with the path integral of this form. And S here is the UV action of my underlying system. Now, computing things starting from this, you know, UV setup is just as hard as, you know, with the standard vacuum QFT. However, we can try to use some effective field theory type of approach here. After all, we want to do hydrodynamics or some extension of it. So we can assume that for some reason there is a good separation of scales. We can split our, you know, psi modes into fast and slow. It's like saying gapped and gapless. So in our case, in hydrodynamics, the slow modes will be the hydrodynamic densities. The fast modes will be everything else. So we started with the Schwinger-Kalisch path integral that we had in the previous slide. And formally, we imagine to integrate out the fast modes, which will lead us to an effective path integral with only the slow modes, with only the, you know, what really is important at a late time, okay? Now, if the separation of scales is good, meaning, you know, the separation is big, then the resulting effective action from integrating out the fast modes will be local. So if this is local, we'll be able to, you know, really use the effective field theory philosophy and try to write down explicitly what this effective action is by knowing its symmetries, constraints from unitarity, causality, and other things. In particular, this action will also include nonlinearities. It will include effects of dissipation, which are important in hydrodynamics. And very, very importantly for us, it will include the effect of stochastic fluctuations, which are necessary in order to do loop effects of these hydrodynamics, of this Fracton hydrodynamics. So maybe I will skip the details about the Fracton story. Let me just say that at the level of this action formulation, we have more degrees of freedom than in the mean field description I outlined before. Now we have a degree of freedom associated to momentum. So this is, if you like, in some sense related to pi I, to the momentum density I said before. This is a coordinate transformation. It will be, so basically this will be the degrees of freedom of an effective nonlinear sigma model, which describes dissipative hydrodynamics. But I think I will skip lots of details, and I'm happy to discuss more after the conclusion. What I really want to point out here is that, before in our mean field hydrodynamics, we had momentum density and the charge density. So one vector and one scalar degree of freedom. Here we have two vectors and one scalar degree of freedom. Okay. So it turns out, trying to construct this off-shell formulation actually requires to have more fields included. And let me just make a broad comment still related to having more fields. If we are away from charge neutrality, meaning if our fluid has an underlying non-zero charge density, okay, then it turns out that those additional fields can be integrated out, preserving locality, okay? So for those that are familiar with it, this is an example of this inverse Higgs constraint or inverse Higgs mechanism. It's a consequence of the non-trigger commutator of our starting algebra. In any case, that's more of a technical note. What I want to say is that after integrating out these fields, we recover the fact that the velocity is a higher derivative object, as we said before. So that's recovered. It's recovered in a fully, geometrical way here. And then, there are other physical informations I'm not going to discuss. The other comment is that if instead we are at charge neutrality, so there is no background density, then the charge and the momentum sector decouple, and we end up with a different theory. The degrees of freedom are different, the modes are different. I don't have time to discuss this too much, but the takeaway of this slide is that if we have a system where some regions have a background non-zero charge, and some regions have a zero background charge, then the mean field hydrodynamics I introduced before is just not valid. You need these off-shell additional degrees of freedom. So it's not just required by writing the action, it's actually a physical necessity if you want to describe such a situation. I'm not sure this is physically too relevant, but at least structurally speaking, it's a very strong example of superiority of this action approach, this geometrical approach compared to the Landau approach. Good. So this is this comment is even before we include the fluctuation effects. Again, this renormalization. But again, these fluctuations are another byproduct of having an action. Now that we have an action, we can actually compute the fluctuation effects. So that leads me to the last part. I'm not going to write down the action explicitly, but I will write really, the essential physics that we want out of it. So if we, there is some non-trigger manipulation that one can make by neglecting suitable interactions at the level of this effective hydrodynamic path integral. And after the dust settles, we basically can rewrite the hydrodynamic path integral as a system of stochastic differential equations. This is actually a standard framework in the context of stochastic hydrodynamics. It's called Martin-Sijarow's formalism. Again, I don't have time to get into the details there, but let me just say that basically what we have, for example, in the conservation here, you see we have, again, the stress tensor, but then we are adding a noise term. Okay, so this is some field which is delta correlated in time and space. It's a Gaussian noise. There are some coefficients for the, for this two-point function, which are determined by the effective action. I'm not going to write them down. But physically, the reason why we have this noise here, it's basically, this is a proxy for the finite temperature fluctuations that will alter the real-time dynamics of our late-time collective behavior. So this noise is really essential to obtain the anomalous scaling that we are after. Good. I had a, well, I have here, so let's see, how many minutes do I have left?
You have certainly 5 minutes, but you can take more time a little. I mean, 10 minutes you can take. Or
okay. Okay.
Yeah.
Good. Okay. So I want to illustrate, this whole story before, getting into the details of fractals. I want to use a much simpler situation to describe the onset of these anomalous scalings and the interplay between nonlinear couplings in the hydrodynamics and the the thermal fluctuations that we have from the action. So I'm going to discuss completely different situation, but again much simpler, which I mentioned in the introduction. So this is just a 1+1 dimension. It's the anomalous non-conservation of a U1 charge. So recall that in 1+1 dimension, the chiral anomaly, it just shows up as a electric field. Okay, and C is the anomaly coefficient. Good. So now again, let's wait some time. Let's say that this is we're interested in the late time dynamics of a strongly interacting system. So let's say that the system has undergone thermalization, and then we can study the hydrodynamics, and again the RG flow of these hydrodynamics. So here, the explicit expression for the current for these hydrodynamics is so here we have let's take the second term. This is just a fixed law. Okay, it just says the current is proportional to the gradient of the charge density. This is Ohm's law. This is the noise. This is the same type of contribution that I discussed here. It is the remnant of the underlying thermal fluctuations. And then we have this term here. This is uniquely determined by the presence of the anomaly. So notice the coefficient here, C, is the same as the anomaly coefficient. And then mu is the chemical potential, which is a thermodynamic, it's a given thermodynamic function of the charge density. Okay, so that's uniquely determined. Good. So now we're going. So first of all, I'm going to motivate a bit in which context this type of system is relevant, and then I will show what happens when we really look at fluctuations. So I would say the primary context is that of in 1+1 dimensions is that of quantum Hall systems. Quantum Hall systems are known on the edge to display propagating chiral modes. These chiral modes, there is a charge, there is a conserved charge. So if these modes are sufficiently interacting, or if we have impurities on the edge, then one can hope that this edge dynamics thermalizes. And if it thermalizes, it gives rise to this late time hydrodynamic behavior. So if we go to one higher dimension, 2+1, there are these so-called surface chiral metals, which basically consist of stacking together a bunch of quantum Hall systems, and then on the boundary along this direction, parallel to the layers, we still have chiral hydrodynamics, and on the orthogonal direction, we just have ordinary diffusion, ordinary hydrodynamics. In 3+1 dimensions, there is the famous chiral magnetic effect, which in the presence of a strong background magnetic field, this generates an equilibrium current. And again, this will lead to a chiral motion. So now going back to the one-dimensional setup. So I'm taking this continuity equation. I am switching off the background. I'm switching off the electric field E. And I'm taking this explicit expression and I stick it in this continuity equation. And that will lead me to a stochastic differential equation, which is here. And upon a few manipulations, I can simplify it in this form. So what do we have here? So the first two terms are responsible for the naive just diffusion. So again, recall I mentioned in the introduction, for a standard system with a conserved scalar density, the expectation from hydrodynamics is that we just have diffusion. Again, this is just a fixed law. But then in this case, we also have a nonlinearity, which is generated by the anomaly. This lambda coefficient is proportional to the anomaly coefficient C. So yeah, if we didn't have anomaly, we wouldn't have this type of nonlinearity. And then this nonlinearity will turn out to be relevant in the RG sense. We can do RG here because we have a noise. We have fluctuations. So this nonlinearity turns out to be relevant. That's just a consequence of doing superficial scaling analysis of this equation. Now, let's say, for instance, we are interested in computing the conductivity for this quantum mole system. And we want to compute the loop corrections to this observable. And then what we see is that if we go to higher and higher loops, there will be more and more singular contributions, more and more singular powers of the frequency, right? That's because this nonlinearity is relevant. So this theory is unstable in the RG sense, in the IR. And again, the signature is in these powers that become more and more negative as we go to higher loops. Okay. So in some way, we need to do a resummation here. So indeed, that's possible. That's because turns out we can map this equation to the Kardar-Parisi-Zhang equation that I mentioned in the introduction. And after a few manipulations, what one observes is that in this one-dimensional system, the fixed point reached by the flow, by whatever flow generated by the noise together with the nonlinearity, leads me to a non-Gaussian fixed point, which is again the Kardar-Parisi-Zhang universality class. In particular, the conductivity that I tried to compute here turns out to diverge with the system size with this universal power, one-third, and the coefficient of the divergence is proportional to the chiral anomaly. So we see here an interesting interplay between a quantum anomaly together with thermodynamic, together with the stochastic fluctuations. Okay. And then in two spatial dimensions, the theory it's not related to KPZ, but it turns out to be marginally irrelevant. So we still have some mild divergences, and then as we go to higher dimension, it just becomes trivial, completely trivial. Yeah, lastly, let me just mention, another byproduct of our prediction is that the dispersion relation, the dynamical scaling for this type of dynamics, instead of having this diffusive damping k square, we expect k to the 3 halves, where again this k to the 3 halves term is proportional to the chiral anomaly. Okay. So looking in the literature and trying to, we really hope that this can be observed experimentally. And we found at least one paper which, from a few years back, which mentions that the magnitude of the damping increases with frequency, the dependence being somewhere between linear and quadratic, which is precisely consistent with this power. So we are now hoping that, with higher resolution in current experiments in several materials, say graphene or even in ultra-cold atoms, we might hopefully be able to have a more certain signature of our prediction. In any case, this is a context, a very simple context where we see the arising of anomalous, finite anomalous corrections to important observables. And the same turns out to happen with fractons in this fractal hydrodynamic context. I'm not going to go through the details. I will end very soon. But what one can observe is that if we look at the nonlinearities in the stress tensor that we find and do this superficial scale counting, we do find that the scaling dimension is relevant. Say, for example, in one dimension, one can try, because these things are relevant, again, there is no diagram, there is no perturbative approach to computing the corrections to the mean field scalings. But, just by doing a crude estimate, we find that the dissipative scaling goes like 2.5. Okay. This should be opposed to 4. Like in the Princeton experiment, I mentioned in the introduction, people observe 4. So our prediction is that if you have an emergent conserved momentum, then the scaling is subject to very strong fluctuations and it flows down to 2.5. So we observe this numeric. Yeah.
Just one question. So here, where is the nonlinearity coming from, or is there what is a specific like you showed there's a specific term there that drives this feature?
Yes. Right. So, for example, this term is the convective term. Like in Navier-Stokes equation, in the conservation of momentum, you have a term in the stress that is proportional to the product of velocity and momentum density, or up to a coefficient is velocity. So that's a nonlinear term. So here, this is very similar. This Laplacian of the momentum is the velocity, and this is the momentum density. So this is really the Fracton counterpart of the convective term. Another nonlinear, this is another nonlinear, this is entirely new type of nonlinearity. It's not there for a non-Fracton fluid. And then, of course, there is the pressure, and the pressure contains, nonlinear terms. In particular, it can depend nonlinearly on the density. Actually, I should say in one dimension, in one spatial dimension, all these nonlinearities cancel out, and the only nonlinearity that remains is this one. So this is really the interplay between this nonlinearity and the noise drives the scaling to this 2.5, or roughly 2.5. So that if you want to try to approach the thing systematically, you should write down an action. You do dimensional counting, and then you'll see that these couplings are relevant. And then you can try to write down Feynman diagrams, and you see that they all diverge as you go to the IR. Now, because at least so far, so actually remember, I mentioned briefly before that in the standard case, for example, here we can compute the exponent exactly. That's thanks to an accidental emergent symmetry in this KPZ fixed point. This is a very well known. This is known since the 70s, probably. Yeah, the 70s, maybe 76. And this allows one to compute exactly this, this type of powers. However, in this situation, unfortunately, we don't, at least that we didn't observe so far. Maybe somebody will be able to catch it. We didn't observe any of such emergent symmetry, so we can only have a crude estimate of these scalings. Nevertheless, we simulated it for the two models I outlined before, and we found a very good agreement with these, even just at the level of this crude estimate. So here we have, basically what we did here, we studied the thermalization time, the scaling of thermalization time with the system size. And it turns out that one can relate it to the power of the dissipative part of the dispersion relation in at low frequency. I'm happy to go more into the details, but in any case, what we see here is indeed a consistency with the 2.5. And then, so we modeled the slight variations of these models, which happen to not have such linearities. That can be obtained if we impose additional parity and charge conjugation symmetries. These discrete symmetries can basically forbid such nonlinearities. But then if we don't have these relevant nonlinearities, we should expect the very late time scaling to recover the mean field exponent that was found in the Princeton experiment. And indeed, in these more highly symmetric models, we recover the exponent. So this is really in full agreement with our effective theory, with all the fluctuation effects. So let me end up here. So we outline a mean field hydrodynamics for these Fracton systems at late time. We then revisited this construction using an effective field theory, some sort of more geometrical construction, which in particular allows to study fluctuations. And we saw that this leads to a breakdown of local hydrodynamics and to a new non-equilibrium universality class, which is related to these fractonic symmetries. So regarding future directions, certainly one obvious thing to do here is extending this study to higher conserved multiples, as well as these subsystem symmetries. I think in particular, this situation, here we have an infinite tower of conserved multiples. So this situation will be much more dramatic. I'm not even sure the randomization group can really be well defined. It is actually an open question in the literature, how to define the randomization group in generic Fracton systems. I think people were able to do it specifically for the toric code using the underlying lattice structure. But here, what we find the interesting thing is that, at least for the dipole conservation, we were able to implement on very general grounds a normalization group flow. So it will be interesting to understand how that extends to more general Fracton systems. And I think we have a perfectly well-defined framework to address that question. The second and very pressing question is to connect what we have elaborated here to known systems. Like I said, we do have a model that we proposed that could be in principle experimentally realized. But it will be also very interesting to understand if there are existing models which in the infrared agree with our predictions. And then lastly, I already mentioned experimental results. So I will end here. Thanks.
Thank you for this amazing talk, Paolo. It was really amazing to hear all this beautiful developments. So let's have some questions. Yeah, so there are many students who actually have read the review and all this. So please ask questions. Okay, so maybe they're shy. So I have some kind of question related to your observation that Tij could be the antisymmetric part of Tij is a total derivative. So suppose you have some boundary, and in the boundary you have some kind of angular momentum or things, then it can interact with this, right? And,
you mean a boundary for the fluid?
For the fluid, and
right.
So there can be further non-trivial effects coming from boundary if the boundary has some rotation, for example.
Right. Yeah, that's a good question. Well, certainly, I don't see how this, dipole conservation can break down in that case. Yeah, that's a good point. I remember briefly thinking kind of along those lines, but it didn't really go somewhere.
Yeah. It seems like there is some sort of a Witten effect or something.
Right.
You can add charge and then that charge can lead to momentum or something like that. So, I don't know. Some funny things can happen because of this. Tij being
right, because so you're saying, just take your action, like for your microscopic system, for your QFT or something, it's defining some, maybe, yeah, inside the sphere. Then do a, just act with the rotation, with an infinitesimal rotation. And then this should lead to some, this must lead to some non-zero contribution, and how to interpret that contribution.
Mm-hmm.
And yeah, like you said, it should be related to charge somehow. It should, yeah, somehow because of this non-trivial commutator leads to maybe a leakage or something.
Yeah.
Yeah, that's a good point. Yeah, sorry, I don't have more. Yeah, so if I, so if this is the, yeah, it should be, yeah, the transformation of the action should be some X dependent and J dependent, like some contribution that's proportional to J, and that's proportional to, actually, yeah, that's proportional to X and to the current J. Now J is a total, right? So, okay, so J is a total derivative. Then I would integrate by parts, which gets rid of the explicit dependence of the position. So presumably, yeah, it should be some cross product of the rotation axis with the charge current.
Exactly.
That's strange. It's a bit funny though that, yeah, what's confusing is, as a consequence of the fact that the action has more symmetries, you actually have less rotation invariance in some way.
Yeah.
It's a bit strange.
But okay, I have another basic question. Like, so you're assuming that there is this translation symmetry that's going to that there's a translation symmetry, but in most cases, I mean, it can be subjected to many kinds of instabilities, right? I mean, that leads to this, especially if you have fractons, because there are some mobility constraints. It's very natural to expect there would be some something that will destroy translation symmetry, or I mean, are there some known examples of fractonic systems where translation symmetry is there in some kind of equilibrium state with translation symmetry?
Right. Yeah, certainly on experimental level, it's very hard to reach exact translation invariance. You can hope that, you might be able to have if you have a sufficiently clean material where your excitations are not too coupled to the lattice vibrations, then momentum is effectively conserved. So that, for example, in graphene, there is this story of emergent fluid dynamics in graphene, and that's because at some temperature regime, people were able to have an effective conservation of momentum, at least according to the general consensus that that's the status. So what what we hope here is that maybe not with the graphene, maybe more likely in the context of these ultra cold atoms, such as in this Princeton experiment, one could be able to have effectively at least in some temperature regime and effective momentum conservation. Basically, the momentum equation is going to have, so in general, you will have a non-zero right-hand side. So you may have a relaxation term, something proportional to pi I. Now, if the relaxation time that appears on the right-hand side is it's much larger than the onset of these fluctuation effects I mentioned, then you will have a parametrically wider time window where you can observe the anomalous scaling. And that's what we're hoping for. That's, for example, what happened in this spin chain, in this non-integrable spin chain. So there is this almost conserved degree of freedom, which is there only at some intermediate temperatures and sufficiently low temperatures and intermediate times. And at those intermediate times, there is this opening of a time window where you observe the anomalous scaling. So basically, we are hoping for a Fracton generalization of this setup.
I see.
Right.
So basically, you can see the avatars of this. So your basic point is that you can see more non-trivial scaling than KPZ type of scaling because of fractons. Essentially, that's your, and
exactly.
Related
so,
to
yes.
fracton physics.
Exactly. So in particular, this diagram. So this diagram again is just any other hydrodynamics other than fractons. It's non-trivial in one dimension and it's marginal in two. In our story, actually, I forgot to mention, the critical dimension is 4. So this curve will do something like that.
With the 2.5 scaling. Okay, 2.5, it is like this.
Sorry. 2.5 is the scaling between frequency and momentum.
Yeah.
It's not represented in this plot. And it's here. It's in one. This is dimension. This is just a cartoon. It's really it really doesn't have much quantitative content. This is just saying the fixed point in one dimension is non-trivial, and the fixed point in 2 dimensions is trivial or marginal. And then, if you investigate what happens here, you will find that the scaling has this power. Now, what we are saying is that in 1D, it's even more non-trivial, like it's even more nonlinear in some sense, because the anomalous correction to the mean field scaling is much bigger. So here it's a 0.5 because it flows from 2 to 3 halves. In our case, it's 1.5 because it flows from 4 to 2.5. Anyway, so yeah, we have a different universality. And then, however, we also have a non-Gaussian universality in 2 dimensions and in 3 dimensions. That's the other novelty of these Fracton systems. And what we expect is that if you are interested in higher multiple conservations, then the upper critical dimension will go higher and higher. And in particular, if you consider these subsistence symmetries, which, by the way, speaking again of relevance to models, these are QFTs that Seiberg and the collaborators have been working on, as well as other groups. Obviously, they have translation invariance. They have these subsistence symmetries which preserve an infinite tower of multiples. So the scaling there is extremely singular, and that's it will be even more dramatic deviation from this picture. I would expect that. Well, I shouldn't say this, but let's say it's not obvious to me that there is even a critical dimension there. It could be that just in any dimension, the IR fixed point is strongly coupled. If it's well defined at all. Yeah, if it's actually well defined at all. And again, I do believe that our framework provides a well-defined setup to try to figure out this question. Because we know exactly what terms. So I mean, the idea here is that, you know, at the scale after thermalization, you have this local hydrodynamics. That's for sure. That's, you know, we have numerical and experimental proof, even in the subsystem symmetry situation, like the much more dramatic situation. So we do know that you can write down a local hydrodynamics. Actually, Andy Lucas has some work out related to it. But then it's interesting to include a translation invariance or some emergent translation invariance, in which case things are still local again, but then the scaling, the anomalous corrections will be, I would expect that they will always be there in any dimension. There is no upper critical dimension. That would be my naive expectation. So yeah, this picture completely breaks down. Yeah, so in other words, we uncovered, you know, if you like, you know, there are all these directions I mentioned that we mentioned about fractons, from, you know, quantum information to elasticity and so on. If you like, this is a further direction, you know, in the context of a non-equilibrium statistical mechanics.
Okay. Okay, thanks a lot again for this.
Yeah, thank you. Thanks for the questions.
For your time.
It was fun.
Okay, so goodbye. See you again, maybe in person in Chennai.
Yeah, hopefully in person. Yeah.
Yes. Okay.
Right.
So goodbye, everybody, and see you next week.
Thanks.
Bye.